Thank you all again for coming back. So we have our first speaker in the afternoon, Eric Chitambar from UIUC, going to talk about non-classicality in quantum networks. Eric, if you would like to have a few words about the TQC conference, please go ahead and please start with your presentation.
Great. Thank you, Motion, very much for the introduction, and it's a pleasure to be here this afternoon. I will come back to the conference at the end, so that I just quickly added that as a final slide. So I'll return to that. But first, we'll get to the good stuff here. So this is some work that I've been doing with two of my students. So I'm going to cover roughly two projects here. One is with Brian Doolittle, and we put a paper out recently you can find here. Another is with Amanda Gato-Lamas. We don't have an archive posting yet, but hopefully very soon. Our paper is nearing completion, so stay tuned for that. And the rough topic that I will be covering here is this notion of non-classicality in quantum networks and its verification. And I'm using this word non-classicality, but it's also commonly referred to, and perhaps you might be more familiar with this notion of nonlocality. So I'll kind of use these terms interchangeably, and there's reasons for adopting one terminology versus another. Well, we'll get into some of that. So let me kind of outline the talk here. I want to spend the first chunk of this just providing an introduction to the topic of Bell nonlocality for two parties, because this is a workshop here, and so I'm not going to take for granted that people are familiar with a lot of these ideas or experts by any means. And so I want to kind of slowly unpack this, and hopefully, if you haven't seen it before, you'll walk away with kind of understanding some new ideas and get excited on this research area. And also, then please, while I'm discussing this again, in the spirit of the workshop, let's keep it informal. Interrupt me at any time. I don't have my screen. I can't see people who are talking, so you're going to have to really interrupt me. I guess a chat box could pop open, but please don't be shy. So after giving an introduction to the topic of Bell nonlocality, I want to discuss its generalization into network nonlocality. So this is a more recent, very active area of research. And then I'll talk about some of the contributions we've made to this area. One is on the detection side, and then another is this notion of Clifford Networks, which is a family of quantum networks. And I'll describe that the result is that we can actually simulate these classically. Okay, so let's begin just talking about Bell nonlocality for two parties. And I want to draw your attention to this review paper, which I was almost, well, it's 8 years old, but it's still, I think, is a fantastic reference on just the topic of Bell nonlocality. So written by some of the experts in the field, and they cover many topics which I guess have been developed since this time of the paper, but it's a really good starting point. So I do recommend you to give that a read. Okay, so what are we talking about here? This is the setting where we have two parties, Alice and Bob. And for the moment, I don't want to say anything about quantum mechanics. All right, so I want to kind of just remove that from your thought process. And we're just going to think about this as a situation where Alice and Bob have two devices. They each hold one device, so we can think of it as a black box. And these black boxes behave as follows. Alice can put in some inputs into her black box. So it accepts an input, X from Alice, and Bob can put in a Y into his black box, and then they get some outputs. Alice receives A and Bob receives B. All right. Now, these are two separate devices. All right. And this is kind of a key point, is that Alice has hers, Bob has his box, and we can make this point more dramatic by imagining that, in fact, they're separated far apart from one another. So Alice could be in China, Bob could be in New York. It doesn't matter. The point is that they each have these own devices, and we're interested in understanding how the inputs and the outputs are related to one another. And more precisely, we can describe the input-output relation by a conditional probability distribution. So throughout this talk, I'm going to use this notation. So this just means it's the probability that the joint probability that Alice receives A, Bob receives B, given that she's put in X and he's put in Y. Okay. And if you think about it, this is pretty much this describes the whole setup, right? Because we're assuming a black box. So I don't want to make any other assumptions about what's going on. So really the whole experiment is described by this conditional probability distribution. That describes everything. If we know this, then
Eric, I have a
know
question.
the whole setup. Yeah, go ahead.
I have a question. So A and B is known to both Alice and Bob, or not?
Okay, so the capital A here, these are the index sets, and we can assume that the index sets are known. All right.
Okay.
But what's not known is the value that Alice will choose from the index set. So that's not known to Bob. And Alice doesn't know what Bob chooses to put in. So she doesn't know which value he chooses.
Okay.
And then likewise, Bob doesn't know Alice's output.
Okay.
And Bob doesn't know Alice's output. And this is the whole idea of keeping them separated. That's why I really wanted to exaggerate this, because we want to think about these as being two labs that are so far apart that there's no communication between them. So they don't know these individual values. That's a very good question. Okay. And good. All right. So the main question that I want to ask, in fact, this is kind of the fundamental question for this whole talk, and maybe even for this whole research area, is can we learn something about what's going on inside these boxes just by studying the input-output distribution? Okay, so this is classical data. I mean, classical data means I can represent my variables in terms of strings of bits. And we want to try to infer something about the physics of what's going on inside these boxes just by studying this probability distribution. All right, and so it turns out the answer to this question is going to be yes. We can infer a number of things. But actually, before I do that, I want to just state two meta assumptions to this question, and these are sometimes often overlooked, so I want to explicitly point them out. First of all, there's some agreed timing for Alice and Bob, and what I mean is that if they're actually going to try to reconstruct this probability distribution, then they have to have some agreed time. So they know that they put in at say time 1 that they will run their boxes at once and obtain one set of output data. At time 2, they choose another input, they receive an output. At time 3, they choose another input, they receive another output. Okay, so there's some timing that's going on here if they actually want to construct this distribution. And then another assumption is the fact that these boxes behave like discrete memoryless channels, right? So we assume there's sort of no memory effect. And then why is that important? Well, because they want to ultimately reconstruct this conditional probability distribution. So they run it many, many times, and then they look at their sample average, and it should converge to this distribution. So they can actually, you imagine they do this many times, and they come back to each other, and they share their data, and they reconstruct this probability distribution, and they say, okay, given this is what we observed after running our boxes for 1 million time steps, and we have accumulated all this data, what can we infer about what's going on inside our boxes? Okay, so that's what's going into this question here. All right, so one possibility is that these boxes have some sort of hidden shared randomness that's actually correlating them. All right, so we can think about this as there's like a random number generator that's outputting some value lambda with some probability, and it's being sent to both the boxes. Or maybe this was done in advance. So when the boxes were initially created, before they were separated, there was some secret instructions that was encoded in both of these boxes. And so now they're correlated in the future. And so now if we write down what will this distribution look like, it'll have this particular form where given lambda, right, then the boxes behave independently. That's why I've written them as a product here. So these are two independent distributions. That's reflecting the fact that the boxes are separate. So once you know lambda, then there's no other correlation between the boxes, so they behave independently. But the point is that this value lambda might be hidden to Alice and Bob. So we have to actually take the average over lambda. So we could think of boxes that have distribution that's described like this. And we could consider all possible boxes having this form, and this will constitute some set. We'll call this local. And the reason it's called local is because really we're thinking about these boxes as behaving locally. Once I know lambda, then they're independent from one another. All I need to do to compute the probability of A is just I need to know what Alice's input was, X. And likewise for Bob, all right? So this forms a set of local distributions. And we can think about this kind of a bit more mathematically. If I first, I'll define the set all, and these are all possible conditional probability distributions, right? So anything I can write, as long as it's a valid probability distribution, meaning that it's a set of non-negative numbers that sum up to 1 if I add over A and B, then that is a valid conditional probability distribution. And I can think of this as like a vector in this large vector space, right? A was the size, these are the cardinalities of my index sets. So I think of this as just being the components of some very large vector, okay, in this vector space. And now I'm looking at a family of vectors that have this particular decomposition. This is the local correlations, and these form a subset in this large dimensional vector space, okay? And in particular, it's a convex subset of all possible boxes. And you can see that the convexity is somewhat easy to see, is if I have two local boxes, right? So if I have two boxes that admit this decomposition, and then I take some mixture of them, say I choose box 1 with probability P1 and box 2 with probability P2, well, then I could just include that 1, 2 variable as part of the shared randomness. So I can mix these things together, and then I get back a box that has the local hidden variable structure. So in fact, the set of local boxes is a convex subset of all possible boxes. But in fact, it's even stronger. It's what's known as a polytope, means that the set can be described as the convex hull of a finite set of vertices, right? So there's like these sharp extreme points here. And so it has this nice geometrical structure. Okay, and this is important because now we can invoke some results from convex analysis. In particular, there's something which is known as the separating hyperplane theorem, which says that if I ever have a convex polytope in some larger dimensional space, I can identify this polytope using hyperplanes, which are just basically the boundaries of this. It's a very nice geometrical picture here. So I can define the set as the intersection of a family of half planes, and each of the half planes are defined by this separating hyperplane. And mathematically, what this is just some linear inequality on the conditional probabilities. So it looks something like this. So if I'm in this set local here, then I have to satisfy some inequality constraint, and the inequality constraint will look like this. So remember, you think of these P, A, B given X, Y, this is like elements of the vector. And so I'm just having some linear combination of these guys. It must be bounded by some value beta. So this is a linear constraint on my probabilities. And kind of more abstractly, or I think a cleaner way of thinking about this, again, if I'm in this kind of higher dimensional space picture, I have a vector P, which is just a vector in the space. And all I'm saying is that I have some constraint on the inner product of P with some vector C. So the C and the beta here are defined by the hyperplane that's bounding my local set. Okay, so hopefully mathematically that makes sense. I'm emphasizing this because in the literature, this is what's known as a Bell inequality. So you may have heard of Bell inequalities in quantum mechanics, but really all what a Bell inequality is it's just a separating hyperplane in this space of probabilities. So a Bell inequality looks something like this. So P now belongs to the set local. So it can be decomposed in terms of this hidden variable structure, and it's just some constraint on it. Okay, so conversely now, this is nice because now we have a way to test whether or not a box is local, right? We just have to check whether it satisfies this inequality or not. And if it violates the inequality, meaning it's outside the local set, then we can't model it. Cool. Is there a question? No? Okay. So yeah, so this inequality is very useful because it gives us a way to test whether or not a given box is non-local. Okay. Good. So let me give an example here. So the most famous example is what's known as the CHSH inequality. And so here our setting is that we have binary inputs and binary outputs, meaning that Alice just chooses from one bit, Bob chooses a bit value, and they get out a bit value. And so it turns out that there's only one family of bounding hyperplanes, and this is known as the CHSH inequality. And it looks something like this, right? It's a linear constraint on the conditional probabilities. So really this, again, the geometrical picture to keep in mind is that the CHSH inequality is like this green hyperplane here. Okay, so it's bounding the set of local boxes from the non-local boxes. And so if we can violate this inequality, then that means that there's no way to generate our boxes using this particular model of shared classical randomness, right? So there's some non-local, some non-classical element that's taking place in order to produce the input-output effects. All right, let me pause real quick and just see if there are questions on the setup so far. Okay, maybe this is old hat for many of you. So if so, I hopefully you're not getting too bored. But I do want to kind of unpack this carefully. One other note on the CHSH inequality is if you were to look at this on say, Wikipedia, and you would see it probably written like this. This is the more well-known form. I've written it here in terms of an expectation, sum of expectation values. And what these are random variables. These are the correlators between two random variables. So A0 is Alice's is the random variable of Alice's output when she inputs 0, and likewise B0 is. So we're multiplying together, right? We're looking at the product. It's the correlator. So we have this particular linear combination of correlators, and they must be bounded by -2 and 2. That's the well-known form. And in fact, this is, from an experimental perspective, this is actually the more important one because, and this goes back to one of my meta assumptions, you don't measure probabilities, right? A probability describes a statistical distribution over many, many trials, right? So really what you physically measure are expectation values, or at least you converge to expectation values in the limit. Okay. Good. So that's so much for like shared randomness between the boxes. Another possibility that could be going on is in fact that there's entanglement that's distributed to the two boxes. So in particular, in this case, we have some density matrix rho AB that's being split between Alice and Bob. So now their two boxes are entangled. All right. And to generate their outputs, what they do is they perform quantum measurements on their respective subsystems of this entangled state. And what I want to do is just quickly do a primer on quantum measurements. Again, this is in the spirit of the workshop. I want to make sure we're all on the same page. So when I talk about quantum measurements in this talk, what I'm referring to are the most general setting, sometimes called POVMs. But you can think of a quantum measurement as just being a set of positive operators. And each of these operators are called effects. All right. And so the positivity means that there's non-negative eigenvalues. And there's also this completion relation, meaning that if I add up all of the elements in my set, all my effects, then I get back the identity. Okay. So this is just a nice mathematical way to characterize the most general measurement apparatus that you can perform. And the way I like to teach quantum measurement to my students is thinking of it as a process of extracting classical information from a quantum system. So, and that's really what you're doing in these experiments here is you have some quantum system that's been distributed and you're trying to extract classical data from that quantum system. And the most general way you can do that is using this POVM formalism here. So I describe this extraction process by these positive operators. And the probability then of obtaining some particular outcome is just given by this inner product. So this is Born's rule here. The picture is very nice. I have my quantum system going in, and now I'm extracting classical data on the output. So it's a transformation from quantum to classical, a QC transformation. And that's facilitated by these measurement apparatus. Okay, but what we're mainly interested here in this talk is extracting joint values, X and Y. And so here now you have Alice is choosing some set of measurements to perform, and Bob's choosing another measurement here to perform. So then we use the tensor product structure to describe the joint effect of Alice getting X and Bob getting Y. All right. Good. So that's what's taking place here. I won't write these down any further because just when you see the data coming out, it's coming from a POVM like this or one of these joint effects. Okay, so here we are. So A, B, X, Y, and this is how they're generating these conditional probability distributions. And the question then is, do these boxes, meaning the joint probability distribution, does it always belong to the local polytope? All right, can we always replace this input-output data with a shared randomness source here? So using a hidden variable model, can we reproduce the input-output correlations? And the answer is no, famously not. And this was what was argued by Bell. And in fact, the set of correlations looks something like this. So we have our local polytope, and there are quantum boxes that exist outside the local boxes. And in particular, one thing you can show is that if it's non-local, meaning it's outside the polytope, and you obtained it by measuring a quantum system, then the state that you measured must have been entangled. Okay, so one way to think about this is non-locality implies entanglement. And again, the meaning of the statement is that if we have boxes that are non-local, then they must have been generated using an entangled density matrix. All right. Interestingly, the converse is not true. So what I mean is that there are entangled states where if you measure them, no matter how you measure them, remember you always have some freedom in the way you measure it, but no matter what choice of measurement you perform, they always will generate a box that lies inside this local polytope. So in other words, certain entangled states can only generate local boxes. And I think this is a super curious fact that we kind of have this one form or roughly of kind of irreversibility or a one directional implication, maybe is a better way to think of it. I want to just spend one slide giving an example of this, and it just indicates how complicated this problem can be. So these are the famous Werner states, and they're called such after Reinhard Werner wrote this paper in the late 80s, or maybe early 90s, I think it's late 80s, where he constructed a local hidden variable model for measuring certain entangled states. And so the class of states he used looks something like this. So you have a singlet, which is a maximally entangled state here. And with some probability nu, you have this state, the singlet state. With probability 1 minus nu, you have complete uncorrelated noise, right? So this is like just all trash here. And so clearly when nu is 1, great, then you have a maximally entangled state. When nu is 0, you have complete mixture of uncorrelated noise. And so the question then is, as we think of nu, as it goes from 0 to 1, when can we generate non-local boxes? Okay, so first of all, before we get to that question, let's first ask, when is this thing entangled, right? So when nu is 1, it's clearly entangled. When nu is 0, it's not entangled. And what you can show, it's not too difficult to do this, but there's a threshold. So when nu is 1/3, anywhere between 0 and 1/3, then in fact it's unentangled. Okay, but above 1/3, then you have an entangled state here. All right, so this is the entanglement divide. But now let's consider the non-locality divide. And so it turns out that, and this is building off some of the earlier work by Werner, that in fact there are local hidden variable models that will simulate all measurement statistics up to this 0.452. This is a numerical result here. This was shown in 2017. I think this is the most up-to-date refinement, but maybe there's another result out there. Again, this is a very kind of one of these holy grail problems, is to understand this Werner state. So forgive me if I'm missing a result, but I think this is the best bound right now as 0.452. And then from the top, there is known violations of a Bell inequality of visibility of 0.702. And so kind of the big open problem is this Werner gap. So we want to know exactly when the Werner state goes from being able to generate non-local boxes to generating local boxes. Okay, so I would state this as an open problem, a fun one to think about. But again, this highlights the fact that this is about the simplest type of density matrix you can come up with. And the problem of deciding whether or not it can generate non-local boxes is still very hard.
Can I ask a question?
Yeah, go ahead.
So about the non-local boxes, are those also numerical results, or are there theoretical bounds on these the distance between the two gaps?
Okay, so what you need, so for the non-local box, like this upper bound, you have to show that it violates some Bell inequality. And so here there is, I guess, like a concrete example of a Bell inequality that's violated at this visibility. Right, so here's like an achievability that's known. And then in the local boxes, the way this is done, they come up with, I think this is done by simulating POVMs by projective measurements. I think this is more numeric here, how they obtain this. To be honest, I don't want to necessarily quote the proof technique here, but because I'm not sure exactly, I can't recall, but I think this was done by simulating POVMs with projective measurements, in which case it's a truly numeric value here. Yeah, I'm not sure if that answers your question or not.
Yeah, it does. Thanks.
Yeah, okay. All right, so one other point I wanted just to mention, just for the purpose of, oh, wait, okay, sorry. So let me wrap up the entanglement part here. So this is all very interesting, but I want to highlight a practical motivation for this line of research. And this has to do with entanglement detection. And so the take-home message here is that if Alice and Bob are able to generate some non-local box here, then they must share entanglement, right? This goes back to this implication right here. So non-locality implies entanglement. So if I do have non-locality, then I in fact must have entanglement. And this is sometimes known as device-independent entanglement witnessing. And it's device-independent because all we're doing is we're using our input-output data to learn something about what's going on in the box. Remember that fundamental question I posed at the first slide. So here we actually are learning something about what's going on in the boxes. We're in fact learning that they were entangled. Or this source, whatever source is correlating them is a quantum source and it's distributing an entanglement. So we can infer that. And it's device independent because we don't actually care about what measurement was performed or what state was generated. We don't even care about that. We just can certify that in fact, there is some entanglement that's between the boxes. And so this can be useful in an experimental setup where, let's say you don't trust your devices, or they're very noisy, or you don't have a good characterization of them, but you want to at least certify that you're doing something quantum in the laboratory. And it's not just all kind of some classical noise. If you're able to violate a Bell inequality, then that's kind of one of the gold seals of success, is that in fact you have distributed entanglement and you verified it without making any type of assumptions on your equipment. All right, besides those meta assumptions I put in, but modulo those, you verify that you have entanglement. Okay, and so this has applications in quantum key distribution, where I think it's probably the most important, because in cryptography, you're very paranoid about the devices and the amount of trust you put in your equipment. So to have a truly device-independent certification of security is fantastic, although maybe overkill, but we can argue that. And then also in randomness extraction. So this is another type of cryptographic application where you can come up with device-independent implementations of this, meaning that you don't necessarily trust your device, but you just have out some randomness at the end of the day that you can certify as being truly random. Okay, and then so I want to just end this kind of introductory, I guess it's more than introductory, but the overview with one other possibility is that the boxes share super quantum resources. Okay, and so what I mean here is that there's something that's correlating these boxes that's stronger than quantum mechanics. All right, so in other words, I can't model this by just having an entangled state that's distributed to the two boxes, but I still want to have some constraint on this device. I don't want it to be all powerful. And a very natural constraint to put on the boxes is that it's in fact non-signaling. And what non-signaling means is that Alice is not able to use this device to send a message to Bob, and likewise Bob can't use this device to send a message to Alice. And a motivation for this restriction comes from special relativity, where we believe if special relativity is true, then the implication is that that messages cannot be transmitted faster than the speed of light. So any theory that respects special relativity then cannot allow for signaling devices. So everything that's correlating these boxes must be non-signaling if we want to stay consistent with special relativity. So this is an interesting question to ask is, if we had more general devices, could we allow for stronger types of correlations between Alice and Bob? And it turns out you can. So in fact, there are super quantum devices that are still respect special relativity, but you can't implement them using shared entanglement. And as an example, if you go to the CHSH inequality, what's known is that, in fact, if you have quantum entanglement, there's an upper bound on how well you can violate, how strongly you can violate the locality bound. But if you allow for these non-physical objects known as PR boxes, for example, then in fact you can go even higher than the quantum bound. Okay, so I think this is, from a fundamental perspective, it's super fascinating because it kind of begs the question, like, why isn't nature more non-local than it is? Why is the quantum boundary here rather than up to the non-signaling boundary? And so there have been various attempts at answering this question, and we've made some progress. I'd say that the verdict is still out, but it is an interesting question from a fundamental perspective. Okay, good. So let me move on now to the next part of the talk, which is moving into quantum networks. All right, again, I want to draw your attention to a review paper. This is hot off the press, actually. So it was published this year, and it covers network non-locality, which has been a very active area of research recently. And this is a very nice review paper, kind of giving the state of the art on this. So I'm not nearly going to go into the depth of what they cover in this review paper. I'm just going to highlight the framework and the general flavor of the problems. All right, so what's going on now? I want you to take the picture we've been looking at between Alice and Bob, and then just multiply it by a number of different parties. So here we imagine we have some network of in this case, 7 agents, right? And they each have their black box. They each can choose their inputs, they get their outputs, and there's some sort of connectivity between them, which is a function of however we've wired this network. Maybe this connectivity is classical, maybe it's quantum. That's what we want to try to understand. So if we switch the type of connectivity between these agents, what type of correlations can we generate? And again, everything can be described by this input-output distribution. So collectively, I have this input vector X, which is all the agents' input, and then we get some output vector A, right? And we can just describe the transitions between them, between the input to output. All right, so that's the kind of the general setup. Here, we'll look at the simplest version of this just to get a sense of what this problem looks like. And this is what's known as the bilocal network. So in the bilocal network, we have 3 parties, Alice, Bob, and Charlie. And now it's characterized by the fact that there's 2 sources that's distributing some sort of resource to Alice and Bob, and then another source to Bob and Charlie. And crucially, that these bilocal networks and these sources are independent. Okay, that's one of the key feature here in this setup here. If these were correlated, I mean, if this was like some mother source that was distributing to these guys, then it would be no different than the standard version. But the fact is, we're taking our source and we're breaking it up into independent parts. And that's where you get some interesting dynamics. So if we write this out, the classical boxes, so if we imagine that each source is distributing a classical random variable, then our joint box now, 3 inputs, 3 outputs, decomposes as follows. Okay, so lambda 1 is coming from source 1, lambda 2 is coming from source 2, and here's the key assumption is that they're independent, so their probability distribution factorizes. And Bob has access to both variables, Alice has access to only one, and Charlie has access to only the other. So it looks something like this. And let me just, as a remark here, I want to say that this setup is extremely relevant to quantum communication setups. If you're familiar with entanglement swapping or quantum repeaters. In fact, this is like the basic building block of a repeater chain, where you have some central station here that's doing some bell measurement. and that will help Alice and Charlie become entangled. So in other words, you have in a repeater setup, you have a source here that's distributing entanglement between Alice and Bob, an independent source that's distributing entanglement between Bob and Charlie, and then Bob does some Bell measurements, which at the end of the day will entangle Alice and Charlie. So I think this is an important network to consider just for practical quantum communication reasons. All right. And now what we see, if we look at this carefully, if we consider all boxes that have this decomposition, now we are no longer in dealing with a convex set. And the reason it's not convex is because if you were to mix two of these, then in fact, you would generate correlation between the two sources. It's just kind of easy to see that, but in fact, we need the independence. So this is non-convex, which makes life more challenging. In particular, we can't use this nice hyperplane separation theorem that I drew out. So there's no way to form bounding hyperplanes. And therefore, we have no linear Bell inequalities to separate the classical correlations, the classical boxes from the non-classical ones. Okay, so there are techniques that are being developed. I'd say this is, again, an active area of research to try and tackle this problem. But one of them, just to give you a flavor, this is one of the first results in this, which is now a decade old, on this problem. It considers the simplest case of, again, bits, so 0, 1 inputs and outputs. And the result is that if this is described by classical bilocal sources, then there's an inequality here. Again, this is a nonlinear inequality that must be satisfied by all classical boxes. And I guess I won't go into this too much, but you can see that it's basically written in terms of the correlators between all three variables. So this is, again, the product of Alice's input, Alice's variable, Bob's variable, and Charlie's variable. So you in fact have this bound on the classical boxes. Okay, this is useful because, again, it gives us something that we can test for. And it, in fact, has been generalized. So now you imagine you have, this would be like a long repeater chain. Okay, so you have n sources in between them, and you want to correlate A and, I guess this would be Alice and Charlie over here, which is node 1 and node n plus 1. But you have all these repeaters along the line here. And again, if we consider just binary input output, then you have this inequality where now we replace the swapping stations in between with their product variable here. Okay, so you have another inequality that's very useful to work with. Right. So a question now is, given this inequality that was proven, what can we infer if in fact we see a violation of it? Right. So the classical bound is 1. So what can we say if we have something that's larger than 1? Well, remember in the two-party case, it was the conclusion was non-locality implied entanglement, right? So then we would conclude that the entanglement was being distributed between the sources. Here, there's actually another possibility. So the first is that the sources are not classical randomness. So that would be that there's entanglement that's being distributed between these. But then another possibility is that the network structure is not an n-local chain. Right? So here we're able to test not only on the type of randomness, but we are also testing on the topology of the network, because this inequality is specific to this being a line, a 1D line of a network. If you had some other connectivity between, say, let's say we had another source here that's connecting A and AN plus 1, then this inequality would be broken. Okay, so in fact, we have two types of testing going on here. So we have a device-independent entanglement witnessing, just like we had in the bipartite case. But now we also have a device-independent testing of network topology. So what I mean is that if you assume that one of these possibilities is not true, right? So if we assume that, in fact, we have classical randomness, then in fact, a violation would indicate that we don't have a chain, that there's some other hidden correlation between our boxes. So again, this has nice application in cryptography. If you're trying to, say, find a side channel between your devices, a hidden side channel that you didn't think was there, if you were to witness some violation, then in fact you would certify that it's not just a simple single source correlator, but there's some other hidden side channel that's correlating your devices. On the other hand, if I assume that my device is a chain, if I'm in the laboratory and I've built it, and I'm pretty sure that if I just look at my device, in fact, it's laid out as a chain, and I violate it, then I can rest assured that, in fact, I have some entanglement that's being distributed between the boxes. Okay, so just some results is that in a quantum bilocal network, you can, in fact, violate this. So you can get a square root of 2 factor. So if you distribute maximally entangled states, you can get a nice violation. So stronger than classical one. And if it's a fully connected network, then in fact you can saturate this. You can get this all the way up to 2. So you have ways to test both assumptions. Okay, so I think I have 15 minutes left. I'm going to go pretty fast here. In fact, the bulk of the foundation of the talk is done. So now I can just kind of go through the results a little faster. So this is now detecting non-locality in noisy networks. And so everything I've been describing so far has been kind of in the realistic scenario where we have perfect sources and perfect measurements and we can reach these bounds. But in practice, you have noise between your source and your measurement device. And so the question is, how do you deal with this noise? I mean, one good thing is that I emphasize this device independence fact. And what that implies is that despite the presence of noise, if we're able to violate one of these bounds, then we can certify that the source is distributing entanglements. All right. So in a sense, it's kind of saying, I don't care if there's noise on my network. I've violated my inequality, then I know I have entanglement. But it's okay, that's true. But the problem is that if this is too noisy, then in fact, your source won't be able to violate unless it's tailored precisely to the noise that you've been given. So the question then is, given some sort of channel noise, how do you maximize the violation of some non-locality bound? Okay, so let me kind of say this again. When I have noise, it's going to change my system such that I will have to choose a particular source state in order to generate non-local correlations between my boxes. So this problem then is an optimization problem, and there's two things that need to be optimized. One is what state we choose to distribute, and then we also have our choice of measurements. So there's two things we need to optimize. So we're interested in this optimization problem. And the question that we asked in the paper I mentioned was, can a quantum computer help here? Okay, and this was, I should kind of back up a second and just say, we were interested in trying to understand variational quantum optimization problems in general. And we were thinking of applications, and we had previously done this work on non-locality. So it kind of seemed like a nice thing to look into. And it was a fun project to embark on. And so precisely what we're trying to do is solve this problem using a quantum computer. And so how might a quantum computer help? Okay, well, so here's the picture. So the first is that you parameterize the state preparation and measurement settings as a quantum circuit. So just focus on this diagram over here for a moment. So remember, we have like two variables here. We have a state preparation variable and we have a local measurement variable. So I can encode my state preparation here is a quantum circuit where I have some unitaries that are preparing my state here, and I have these parameterized by some rotation angles. And then likewise on my measurement device here, you have some parameters here that you can play with, and then that chooses your measurement basis. So I can group everything together, and in between is the noise, and you end up getting something that looks like this. And so now we have some variables that we can optimize over. And so this is where we use the quantum optimization idea, the variational quantum optimization idea. And just at kind of a high level, how this works is we use a gradient descent approach. So you first choose some random settings for your sources and your measurement devices. And then you can then run your circuits and obtain your output distribution. And then you can test how well this output distribution works, and using this cost function. So this locality inequality, this is where your cost function goes. So that non-linear Bell inequality, for example, would go in here. And then you do just basically like a gradient descent here. So you differentiate with respect to theta, which is these variables here in your circuits, and you try to maximize then. So you move to the level of steepest descent, then you plug those new variables back in here, and you run the circuit over and over again. Okay. So here's just some results on this. So we found that this actually works pretty well, this method. We checked against depolarizing noise. So there's two different comparisons that we did. We did single qubit noise. So this is where there's just a noise on one arm of your network. So this is now in the bilocal setting. So just one of your connections is very noisy. The other one is clean. And we compare that to the uniform qubit. So each of the connections is noisy. And you can see that, in fact, I mean, the interesting thing is the green boxes versus the dashed green. So we know some theoretical results here. And so that's the dashed green, but in fact, our VQO method coincides like exactly with it. So that was very encouraging. And you might be wondering like why there's a dip and then a recovery here. It's just the way we parameterize this depolarizing noise. I'm assured that it makes it easier to write out the code when you do it this way. Here's the nice coinciding between our numerical results and what's known theoretically. And so I guess this is promising because although there are theoretical results, the whole idea is that, well, if we now go up to larger networks where we can't do the theory, we can actually use this method because we have kind of a proof of principle demonstration in the simple case here. Okay. And then we also looked at amplitude damping channels. So we have similar results for amplitude damping. But one thing I want to kind of point out, what was a cool discovery, which we didn't anticipate earlier on, is now this is looking at the optimization of your state inputs. And so what we found, in fact, is that you can get higher scores, or rather, you have more robustness to amplitude damping if you use non-maximally entangled states. So let me just go back to the picture here. So remember, you have some source here that's preparing an entanglement for the two boxes. And it turns out that if these are amplitude damping channels, then your optimal strategy for certain damping parameters ranges, your optimal strategy here will be to not use maximal entanglement between Alice and Bob, but you use some sort of weakly entangled state. And that, in fact, you're able to tolerate larger noise in your channels. So that's not, I mean, similar results have been known, I would say, but in this case, this was the first time we found it in the channel noise model. Okay, good. So I see I'm at 12:52 right now, or 1:52 Eastern time. Let me pause. I mean, I'm okay just kind of answering questions and skipping this last part here. I don't know. Motion, what do you think? What would you recommend for time here?
Well, I have one question.
Yeah.
I think I have a hand raised by Anurag. Do you have a question?
Oh yeah, but please go ahead. I mean,
go ahead. You go ahead.
Okay, fine. I'll do that. So, hey Eric, very nice talk.
Thanks, Anurag.
So, one of the applications of classical, the usual two-party Bell inequality is certified randomness.
Yeah.
I mean, you can be sure that you have some totally safe randomness with you, Alice and Bob. So what happens in this case? Like if you saw a violation of this multi-party Bell inequality, could you get an understanding of that? Like you have some form of randomness shared between parties in some sense.
Yeah, it's a very good question. You could probably make some let me go back to this. Right, like here. I think if you made an assumption that, I guess this is maybe the crucial assumption. I mean, you have to assume that you have this line topology here. Then I think you maybe could make some assertions about certified randomness. But I don't. Again, it's up to this module of this assumption that you don't have any side channels between the different nodes.
I see. Okay.
Yeah. Okay. So I'm gonna leave that as a fantastic open question. I mean, I haven't seen it resolved, but it's a good question. But I think you could do something. But again, you have to add some assumptions because now you have the network topology to deal with as well.
Got it. Yeah.
Yeah.
Thanks.
Okay.
So I have a question. If anybody else.
Yeah.
So I think it was a slide before this or after that you wrote this expression for I and J.
Yeah. Here, maybe, or I think it's before this here.
Here.
Yeah.
At the bottom. So is it usual that you see these kind of expressions here with the summation at the bottom or the summation for J22?
Is this usual?
Yeah. Because this reminds me of some sort of Fourier expansion for these quantities. This sort of summations appears there. I was wondering if there's any connection there.
Yeah. Okay. So you can write this. So notice this is written in terms of the correlators here, right? But I could also express it in terms of, oh, I guess I kind of have it there, right? So I'm expressing the correlators in terms of the conditional probabilities. And so I think maybe that's one way to think about it, is that going from one representation to another is done by this Fourier transform. So this, I think, is standard of going from a correlator representation to a probability representation with doing this type of Fourier combination. And now for actually forming J22 and I22, yeah, I guess it's, I don't know if I'd say it's common. I mean, this inequality is certainly common in the study of bilocal networks. But I guess there's probably a deeper answer here to that question that you're raising.
Thank you so much.
Yeah.
It was a great talk.
Thank you.
I have one question.
Yeah, go ahead.
May I ask? Nice talk, Eric.
Thanks.
If you go back to the PR box, can you say a few things about that?
Sure. Yeah, I went quickly here.
Yeah.
Okay, so yeah, this PR box is an interesting beast. If you look at it, so what's happening? So it's a random coin flip, but basically the output of Alice and Bob are going to be perfectly correlated, meaning it's going to be, they'll have 0, 0 or 1, 1, like uniformly. It's like a coin that they share, provided that the product of their inputs is equal to 0. Right, so it's like you and I share a coin, right? We flip our coins, and they're always going to be both heads or both tails, unless we initialize our inputs as 1. If we both choose 1 as our inputs, then what happens is that mine is head and yours is tails. Right? So that you would anti-correlate it only if they both choose to put 1 into their boxes. Otherwise, they're perfectly correlated. And it turns out that this is actually very hard to simulate. Well, it's impossible to simulate using entanglement. You can't simulate that strong of a correlation. Okay, so that's how the box behaves, but it's non-signaling, meaning that if I just look at my outputs, I'll always just see, it'll just look like a random coin flip to me, heads, tails. So no matter what your input is, no matter if you choose 0 or 1 inside to your box, it'll look completely random to me on my output. So in fact, there's no way for you to send any information to me because it just looks like pure randomness, a pure random coin flip on my end. But it turns out that in fact, this if you define this thing, then in fact, you can just see that you in fact saturate the CHSH bound here. So you get a 1 here. And this is something you can't do with entanglement.
Okay.
Yeah. So it's in this sphere of kind of like a generalized probability theory of nature. If all I want to do is describe nature with probabilities, I can come up with something that respects the constraints of special relativity, but I have no quantum model for it, meaning using principles of quantum mechanics.
Okay, thanks.
Great. Okay, and I am going to end on I'm sorry I didn't get time to talk about the Clifford Network. I'd be happy to talk about that later. But what I wanted to do is